Okay, so good day, everyone, and happy Thanksgiving week. So we have our last second last talk of the semester, and there's work by Paolo Santini, who's going to give a talk on the new formulation of linear equivalence problem and borderless signatures. So Paolo is from Italy, and so he's at the University of the Marche, and we are happy to have him here with us, recording, giving his talk on this beautiful work. So the floor is yours, Paolo.
Okay, thank you, Francesco, for the introduction, and also thanks for the invitation. I spent some time in Florida in FAU, so I was visiting PhD students for 2 months, and then I was a postdoc working with Edoardo Persighetti for more or less 5 or 6 months. I actually had some really good time in FAU, so I'm really happy to be back, even if it's just virtually. And I'm really happy to give this talk, which, yeah, I mean, the talk is about LESS, a signature scheme. It is my favorite signature scheme. It is a work I did with Edoardo and a lot of other people. And actually, you know, LESS basically was born in FAU because while I was in Florida in FAU, I talked a lot with Edoardo about code equivalence, and in the end, we came up with this scheme. And so in this talk, I'm going to present some recent results on code equivalence. I hope the talk will be interesting for you. I tried to essentially squeeze 2 papers in this talk. So there's a lot of things to talk about. I hope you can get the main idea. So, okay, let's start. These are the main contents of the talk. So I will start by giving some basics. So I will recall the framework of signatures built from zero-knowledge proofs using group actions. Then I will tell you some basics about code equivalence and how you can use this problem to build LESS, which is the acronym of linear equivalence signature scheme. And then finally, for the second part of the talk, I will focus on recent results, and in particular, I will talk about 2 recent papers. The first paper is a paper that Edoardo will present in AsiaCrypt next week, probably, if I'm not wrong. No, maybe at the beginning of December. And another paper I will refer to is a paper that you can find on ePrint, and it is a joint work with Tunchu, Edoardo, and okay, the last author is me. Okay, and in particular, I think these last 2 results are really interesting because essentially what we did in these papers is finding a new formulation for the code equivalence problem. And this formulation, first of all, gives us a new insight on the problem. And using this new formulation, we can achieve very small signatures. So finally, we can claim that LESS is a scheme with very short signatures. Okay, before I start, I would like to make very clear that in this talk, I will be informal in the sense that I will try to keep the talk as less boring as possible. Which means that I will skip a lot of details, I will skip a lot of formal and technical definitions, etc. Moreover, I will present these recent results using a simplified description, because I mean, putting all the details, all definitions in the talk would have result in something really, really boring. So if you want to know the full details about these techniques, you should really read the corresponding papers. Okay, so let's start by recalling the framework of signature schemes built from the Fiat-Shamir transformation. The basic ingredient is that of interactive proofs. So we have 2 parties, a prover and a verifier. These 2 parties exchange messages, and the aim of the protocol is that of allowing the prover to prove the knowledge of some secret. So the prover, the guy on the left, possesses the secret key, while the verifier possesses the public key.
冇辦法㗎，中六嗰啲冇得運彈，因為氣中六就嚟㗎嚇，氣中六啦，冇辦法，氣中六攞條 CD 咁樣算啦，我都唔使揀啦，物理係算㗎啦，所以我不如翻學不如自修嘅物理係算啦。
Excuse me.
反正
Okay.
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 Okay, I will continue. Okay, so the aim of this protocol is that of, I mean, the prover will prove knowledge of the secret. This is a very general description. And the idea is that essentially the verifier sends challenges to the prover. So the prover is asked to reply to some random challenges. At the end of the interaction, the verifier will check the validity of the received messages. When we apply the Fiat-Shamir transformation, essentially we make the protocol non-interactive. The idea, in a nutshell, is that of replacing the verifier with a random oracle, a hash function, for instance. So the idea is that if we apply the Fiat-Shamir transformation to a zero-knowledge protocol, we obtain a signature scheme where the signature is composed by the transcript of the protocol, so the set of all messages. Okay, this is very informal and super quick, but I mean, this is how the Fiat-Shamir transformation works. And so the signature is the set of all the messages that are exchanged by the parties. So obviously, we want to have short signatures, so we want to have short messages. The second ingredient is that of cryptographic group actions. By cryptographic group action, we mean a group action. So we have a group G in which we have an operation, which I'm indicating with the circle. We have X, which is a set of objects, and the group G acts on X in the sense that we can apply elements of G to the two elements of X, and the effect is that of moving these objects. When I think about group action, normally I think about the Rubik's Cube. So imagine that G is the set of all possible moves that we can apply to the cube, so rotations, etc., while X is the set of all possible configurations. We can start from any configuration, we can apply any move, and we will find another configuration for the cube. And obviously, we also want the group action to be efficiently computable, because we want our protocols to be efficient. Speaking about the Rubik's Cube also gives us an idea of the hardness of the problem. I'm not able to solve the Rubik's Cube, so for me, the Rubik's Cube is an hard group action, but we know that there exist people that can solve the cube very efficiently. When we want to use a group action in cryptography, obviously we want the problem to be hard, and in particular, the problem can be formalized as the vectorization problem. So essentially, we are given two elements of the set, X and X prime, and the problem asks to find a group element G such that X prime is corresponds to the application of G to X. So we need to use group actions in cryptography. We need problems for we need group actions for which the vectorization problem is hard. Okay, now we can apply, we can consider group actions to build zero knowledge proofs, and actually the resulting protocol is very, very easy. Again, I will present the general protocol. I will not enter into details, but imagine this situation. The secret corresponds to an element of the group, so the secret is the secret key G, while the public key is a pair of elements X and X prime, where X prime corresponds to G star X. The protocol starts with the prover sampling a random group element, G tilde, and G tilde is applied to X, obtaining X tilde. This X tilde corresponds to the commitment. Now, so basically the verifier knows X, X prime, and X tilde. Now the verifier will sample the challenge, and in this case, the challenge corresponds to a binary value, so it's either 0 or 1. When the challenge is equal to 0, then the prover will reveal G tilde. And so the verifier can check that the commitment is indeed obtained from X. If instead the challenge is equal to 1, then the verifier can indeed check that the commitment can also be obtained starting from X prime. So in the end, you have this graph, and the proof is obtained considering the path on the left or the path on the right. Obviously, the verifier will not reveal both paths, otherwise the secret key can easily be computed. Okay, so this is very, very general. There are also some other general considerations that we can consider. So for instance, if we start from this simple protocol, this simple sigma protocol, then we can consider parallel repetitions to amplify the challenge space, and so also to amplify the sumness. There are also some optimizations that one can use using hashes, seeds, etc. In any case, the important thing is that the public key size will correspond to the binary size of an element of X, while the signature size will have this formula. And essentially, in this formula, we can see two main components. The first component is independent of the choice for the group action. It depends only on the setting for the protocol, so the number of parallel repetitions, etc. While the component on the right really depends on the group that we use. Okay. So yeah, this is very, very general, and we can use our favorite group action in this framework. Obviously, the choice for the group action has some impact on the performances of the scheme, because the public key size depends on X, while the signature size depends on the elements of G. Okay, now our favorite group action, well, at least my favorite group action, is the group action resulting from the code equivalence. So let me tell you a few words about code equivalence. We are speaking about linear codes defined over finite fields. So by linear code, we refer to a dimension, to a subspace of the vector space fq to the n. We say that the code has dimension k if the subspace has dimension k. We represent codes using generator matrices. So given a code, we say that a generator matrix G is a we say that a matrix G, sorry, is a generator matrix for the code if the code is the row span of G. So all the code words are generated by linear combinations of the rows of G. We see that we can have multiple generator matrices because starting from any generator matrix G, we can apply a change of basis, and the new matrix S times G will be another generator for the same code. And among all of these generator matrices, sometimes we consider the systematic form, that is the generator matrix having the identity on the left. And to compute the systematic form, we consider a function as f. And it can be easily seen that this function is invariant under changes of basis. So this means that if we start from two different generators for the same code, when we apply the systematic form, then we obtain the same matrix in systematic form. Yeah, this is more or less everything we need to know to study the code equivalence problem. Now, when we consider codes, normally we speak of some metric, in the sense that we have this code, so we have this set of code words, and we want to find, we want to consider a function that we can use to measure the distance between code words. We consider the Hemi metric, so I would say the simplest metric we dispose of. And now we consider isometries in the Hemi metric. We can start with an example considering permutations. So we have Sn, which is the symmetric group. We see the elements of the group as permutations. And the application of a permutation to a vector simply corresponds to a shuffle in the order of the elements. So we obtain a new vector with the elements having a different order. We can also apply permutations to codes. So if we start from C, we obtain C prime, which is a new code. And essentially, the new code is obtained by applying the same permutation to all the code words. it's easy to see that if C is generated by G, then C prime is generated by pi of G. And obviously, we can also apply a change of basis. Now, if we consider what happens to a code when we apply the permutation, the situation will be something like will be similar to the one you see in the slide. So obviously, this is a toy example. Imagine that the codes we use in cryptography are much larger. We have many more code words. But essentially, what happens is that the permutation will change the labels for the code words. But from a geometrical point of view, the code remains the same, which means that the distances between the code words are preserved, and also the weights of the code words. So yeah, in the end, if we have two equivalent codes, they are really the very same code, because geometrically they are the same. The only difference is in the labels we use for the code words. So this leads us to the definition of the permutation equivalence problem, which is very, very easy. On input two codes, C and C prime, the problem asks to find a permutation mapping one code into the other. Normally, we use generator matrices to represent codes, so we can also consider the linear algebra formulation. So we are given G and G prime, which are generators for the two codes, and the problem asks to find a change of basis S and a permutation matrix P such that G prime is equal to SGP. Okay. We can also generalize the notion of isometries. We can even consider non-linear isometries, but for this talk, we will focus to linear isometries. And so we can consider the more general case of monomials. So we have Mn, which is the group of monomial transformations. A monomial is a permutation with some scaling factors. So you see that to define a monomial, we need a permutation and also a vector V, where it's a multiplicative group of the finite field. So essentially, a monomial changes the order and then applies some scaling factors. Again, we can apply a monomial to a code, and so we obtain a new code C prime. And we can also define the corresponding problem, equivalence problem. The problem is called linear equivalence problem, and it is a generalization of PEP because permutations are a special case of monomials. We can see that a permutation corresponds to a monomial in which all the scaling factors are equal to 1. Okay, now this is the first detail I need to clarify. In all our papers, we speak of LEP, so we consider the linear equivalence problem because this is the most general case. However, for this talk, I will focus on the permutation case because this is a bit easier to speak about, okay? But if you read the papers, then you will find everything in terms of linear equivalence problem. Okay, now let's see how we can obtain a group action from the code equivalence setting. So we can start from a code C, and then we consider the orbit of C under the action of Sn. It's easy to see that this is a transitive group action, where the group is the symmetric group and the set is the orbit. The application of a group element is simply the application of the permutation to a code. And we see that the group action is transitive because for any two codes in the orbit, then we know for sure that there exists a permutation mapping one code into the other. Obviously, all the properties apply also to the case of monomials. Okay, so we have a group action. We have seen that this group action possesses all the properties that we need. It can also be seen that we know that there exist R instances, in the sense that we know about instances of the problem that cannot be solved efficiently. Again, there are many details here. I will not have time to explain to you all these details, but in any case, we know that if we are looking at the permutation equivalence case, then we need self-dual codes, so codes that are contained in the dual. While if we consider the more general case of linear equivalence, then even using random codes is enough, given that Q is large enough. But okay, so we have all the ingredients that we need because we have a group action. We know that we can compute this group action efficiently because it's just linear algebra. And also this group action corresponds to an art instance of the vectorization problem. So we can put the code equivalence in the framework of Sigma protocols from group actions, and we can obtain a signature scheme. This is what we did for less. So in a nutshell, the basic zero-knowledge protocol works as you can see in the slide. The secret is a permutation. The public key is a pair of codes, C and C prime. We know that C prime is equivalent to C. The commitment is another code. You see that C tilde is a random code which we sample from the orbit. And actually we sample tau, and then we apply tau to C. And then we have two challenges, and the responses will either be tau or tau prime. So yeah, this is how we can use code equivalence to build a zero-knowledge proof. And so we can apply the Fiat-Shamir on top of this and obtain a signature scheme. When we use codes, normally we consider generator matrices because it's easier to work with matrices. So in practice, to instantiate such a protocol, we will use two matrices, G and G prime. G prime is obtained by doing the systematic form of pi of G. The systematic form is employed for many reasons, but the first reason is that if we have a matrix in systematic form, we don't need to publish the identity, and so we reduce the public key size. Okay, now to prepare the commitment, we first sample tau, and we compute G tilde, and then we commit to the hash of the systematic form of G tilde. So you see that the blue path corresponds to the response for when the challenge is equal to 0. When the challenge is equal to 1, the response provided by the prover is tau prime. And in this case, tau prime is applied to G prime. And then to check the commitment, the verifier needs to do a systematic form and one hash computation. Yeah, this is how less works. Okay. Now, before we analyze the performances of this very simple protocol, there is something we need to understand because I mean, the improvements I will present in the second part of this talk really depends on this very simple reasoning. If you consider this protocol, you see that we are doing the systematic form. We know that the systematic form can be computed efficiently, but the cost of any systematic form computation is cubic in the code length because we need to do Gaussian elimination. So, you know, yeah, this is a polynomial complexity, but it's not exactly efficient. So why are we using the systematic form? So we can generalize the situation in this way. Assume that you have two codes generated by G and G prime, and you want to communicate a solution to the permutation equivalence problem. So basically, you know that G prime can be written as S times pi of G. So the most trivial way would be that of giving S and pi, so that the verifier can apply S and pi to G and check that indeed this computation leads to G prime. However, this is not efficient from a communication cost point of view, because you need to send S, and S is a matrix. So communicating S is really costly. We can get rid of S and we can just communicate pi, because when we apply pi to the matrix G, then the verifier obtains a generator matrix for the very same code which is generated by G prime. So essentially, G prime and pi of G generate the same code. But these two matrices are different because of a change of basis. When we use the systematic form, we get rid of this change of basis. This is the main idea. We have two different generator matrices for the same code, using the systematic form, we can transform both matrices into the same matrix. So the idea is that of using the systematic form as a sort of representative for all generator matrices of the same code. In other words, we use the systematic form because it is an invariant. It is an invariant under changes of basis. And this is really, really important because later on I will describe to you two invariants that we can use to reduce the signature size. Okay, so this is the situation with less. I mean, this was the situation with less before the two papers I already mentioned. We see that the computational complexity is cubic because we need to do systematic form computation. The public key size is quadratic in the code length because we need to publish G prime. And if we consider the size of of tau prime, we see that it is n log n for the permutation equivalence case and n log n plus log q minus 1 for the linear equivalence case. Now, to see if these numbers are good, we can consider as an example the parameters for less NIST category 1. We see that we need Q equal to 127, N is 256, and K is 128. So if we consider the permutation equivalence case, then each group element has a size of 256 bytes. If we instead consider monomials, then the size increases and becomes 480 bytes. And actually, this is a lot because 480 bytes is more or less alpha kilobyte. So it's clear that if we consider, if we do the Fiat-Shamir transformation of this protocol without any improvement, then we would end up with a signature scheme in which signatures are really, really large. Because imagine that each time the prover replies with tau prime, this message has a size of alpha kilobyte. Using the first idea I will mention to you, we can halve these numbers. So instead of, for instance, 480 bytes, we can reduce this number to 240. However, using this new idea, the size becomes really, really smaller, because for both problems, we can use only n bits. And so instead of 480 bytes, the communication cost is reduced to only 32 bytes, which is a really good improvement. Okay, so this is the situation. This table is a little spoiler of what we will see. And now I will try to explain to you the ideas behind these two techniques, which I call the information set linear equivalence problem and canonical form linear equivalence problem. And in particular, I will try to do this by describing only the canonical form case, because the information set case is a special case of this one. This is the roadmap for the second part of the talk. Okay, so let's start with the basic ingredient for this canonical form thing, which is the notion of equivalence relations on matrices. So we consider k times n minus k matrices, and we consider F, which is a subset of Sk times Sn minus k. And moreover, we consider 4 possible cases for F, in the sense that we consider F as the vector space of two groups of permutations, but we allow some of these groups to be trivial. Using F, we define an equivalence relation on k times n minus k matrices. And so we say that given two matrices A and A prime, they are equivalent with respect to the relation Rf, if they can be expressed as you see in the slide. So if we can say that A prime is equal to some permutation of the rows, P rows times A times some permutation of the columns, then these two matrices are equivalent. For instance, if we consider the most interesting case in which both sets are non-trivial, then really A prime and A are equal up to a permutation of the rows and a permutation of the columns. Starting from any choice of F, we can define what we call the canonical form. Canonical form is a function. The input for this function is a k times n minus k matrix, and the output is a matrix with the same dimensions. And we want some properties to be satisfied. So, for instance, we want that the canonical form can be computed efficiently. We want that the canonical form corresponds to the output of the canonical form, corresponds to the input matrix times a permutation of the rows and a permutation of the columns. And moreover, we want that for any two matrices that are equivalent with respect to Rf, we have the same canonical form. So I think you can already see that the aim is that of using canonical forms as a sort of invariant. Okay, in the formal definition in the paper, we also consider the case of failures, because the canonical form may not exist in some cases. This is not an issue. It's very easy to deal with the existence of failures. But in this talk, I will forget about failures, okay? Again, this is another simplification I'm considering. If you want to see the details, you shall really read the paper. Okay, let's make some examples. So, for instance, let's consider the case in which the first set of permutations is trivial. So we say that for this case, two matrices are equivalent if and only if they are equal up to permutation of the columns. We define some lexicograph ordering on vectors, for instance, the one you see in the slide. And now computing the canonical form, sorry, is very, very easy, because on input A, the output of the function corresponds to A times P calls, so some column permutation. And we choose the permutation such that the columns of A star are in lexicograph order. Okay, we see that obviously this function satisfies all the properties that we want, so we can compute this function efficiently. It possesses the invariant properties that we need, etc. So yeah, I mean, this case is not really interesting. This case actually is more interesting because in this case we don't have trivial sets, and so F is the product between Sk and Sn minus k. We can define a canonical form also in this case. And to do this, we also need some lexicograph ordering on multisets. So, for instance, the one you see in the slide, on top of the slide. And we can define a canonical form essentially doing two operations. In the first step, we sort the rows so that the multisets formed by the rows are in ascending order. And then we sort the columns so that the columns are in ascending order. We can consider an example. So imagine that we start from this matrix, which is a 3 times 4 matrix. I'm going to use colors to specify how permutations are applied. Okay, this is the matrix with the multisets. We will sort the multisets. So in this case, the new order will be blue, green, red. And then we apply the same permutation to the initial matrix. So yeah, this operation corresponds to step 1. We found a row permutation. Then we consider the columns, and I'm going to use colors again. We sort the columns so that these vectors are in ascending order, and this is the final matrix. So you see that the new order is green, blue, brown, red. So in the end, the matrix on the right of the slide corresponds to the output of the canonical form. And you can see that, again, all the properties that we want are satisfied, because obviously we can compute this efficiently in polynomial time. The output of the canonical form is really an application of two permutations, one row permutation and one column permutation, etc. Actually, in this case, we can have failures, but again, failures can be tolerated, so it's not an issue. And so, yeah, I mean, I show to you an example of canonical forms. Obviously, there may exist other functions, so we can define canonical forms in a different way. It doesn't matter. The important thing is that we know that functions with the desired properties exist. And actually, finding such functions is really everything that we need for to use this new formulation for the code equivalence problem. Okay. Now, let's forget about canonical forms for a moment, and let's see something that I called splitting a permutation. So we consider permutations, obviously, and we represent permutations using matrices. So every permutation is a n times n matrix P. Now, we are going to split the permutation in the sense that we have the information on how the permutation acts, and we divide this information into, I would say, 3 main pieces. So the first piece of information corresponds to which columns we place on the left. So imagine that we are applying this permutation to a matrix. So some columns will be moved in the first k positions. Some other columns will be moved to the last n minus k positions. The first information corresponds to which columns go to the left. Then we have the second piece of information, which tells us how the columns on the left will be sorted. And then the final piece of information corresponds to how the columns on the right are sorted. If you think about it, really, this is what a permutation does. Now, for any piece of information, we can consider a permutation matrix. So, for instance, for the first information, obviously, okay, I have examples about this, so I hope the reasoning is clear enough. But in any case, for any piece of information, we can associate a permutation. For the first information, so which columns go to the left, we can define a special permutation, which I will call PES, where ES stands for information set. And then we have the second information. The corresponding permutation matrix is P rows, and for the third one, the associated permutation matrix is P calls. And in particular, it's easy to see that for every permutation, we can consider this splitting. So given any P, we can always find a P, ES, P rows, and P calls such that the equation in the slide holds. Now, I'm using the inverse of P rows, and the motivation will become clear in the next slide. But in any case, this is something that holds for all permutations. Okay, now let's consider the action of these permutations piece by piece. So we first consider the application of PES, and the application will look like this. So we start from a generator matrix G, we apply PES, and in the end, we can divide the matrix we find into 2 main parts, the part on the left and the part on the right. Okay. Now, if we do some linear algebra and we consider also the action of P rows and P calls, with simple computations, we find that, again, we can divide the resulting matrix into 2 main components. The component on the left is given by Gj times the inverse of P rows, and the one on the right contains P calls. So you see that essentially, using P rows and P calls, we found a permutation acting on the left and a permutation acting on the right. Now we can do the systematic form of this. We can even consider change of basis. It doesn't matter because we know that the systematic form is uninvariant under changes of basis. So after systematic form computation, we have the identity on the left. And on the right, we have the expression you see at the bottom of the slide. So we have P rows times something times P calls. Okay. now let's remember this property. So let's consider some g prime which is equal to SGP. So this g prime is equivalent to some generator matrix G. We consider systematic form of g prime and we obtain identity, and A. A is the matrix given by P rows times the blue matrices times P calls. Okay, now imagine that you have this matrix P star, where P star is equal to P, with the only difference that instead of P calls, we have the identity. We can apply P star to G, we can do systematic form, and after all of these computations, we end up with a matrix where the non-systematic part is equal to A times the inverse of P calls. So basically, the matrix we find is equal to A up to a column permutation. So what happens is that essentially, let's look at P star. It's clear that P star is missing one piece of information, because P star is missing the permutation P calls. So we can obviously represent P star using a smaller amount of bits, because essentially we are not sending information. If we apply P star to the matrix G, we obtain something that is different from the systematic form of G prime, but it really looks like the systematic form of G prime. The only difference is in the application of this permutation on the right. The idea is that using canonical forms, we can get rid of this discrepancy, and so we can find the very same representative for the systematic form of G prime and the systematic form of G times P star. That's the idea, but I will be back to this in a few minutes. We can also consider a more powerful situation. So imagine that we also get rid of P rows. So we only send PES. If we do this and then we apply P star in systematic form, the matrix we obtain, I'm speaking about the non-systematic matrix, the non-systematic part after systematic form. The matrix we obtain will be equal to A up to a row permutation and a column permutation. So again, we found a different generator matrix, but the matrix we found really looks like the initial one. The only difference is in the application of permutation on the left and a permutation on the right. So again, if we use systematic form, we can really acknowledge that the two matrices are literally the same up to these two permutations. Okay, so we can start seeing how all of these things apply to the setting of less. So imagine that you have these two matrices, G and G prime. The prover knows the solution P. To show knowledge about the solution, the prover will send P star, only P star, where the information on the column permutation is missing. Verification now becomes a bit more complicated because doing systematic form is not enough. But the verifier will only apply P star, then it will compute the canonical forms, and finally the verifier will check that the canonical forms are really the same. You can easily see that in this case the communication cost becomes only K times log n. And the idea is that, so when I first presented less, I mean, if the prover replies sending P, then the prover needs to tell needs to specify the action of the permutation on all coordinates. If we do this instead, the prover needs to specify the action of the permutation only on K elements. And so the size for P star becomes K log n. In this case, we are using two invariants. So we have the invariant for the change of basis, because we have the systematic form, but we also have the invariant for column permutation. So the idea in the end is very, very simple. The prover, we can reduce the communication cost by not sending some information. So essentially, the prover does not send the full P, but he sends only a truncated description of P. But verifying the validity of the response is possible because of invariance. In this case, the invariant we use is the canonical form. Okay, we can obviously the very same setting applies also to the case in which P star is equal to PES. And actually, in this case, the communication cost is really, really reduced. And so the size is N. Because in this case, the prover is only telling which columns go to the left. So you can imagine that the response given by the prover is a binary vector in the positions where the vector is equal to 1. I mean, for every 1 in the vector, then we know that the corresponding column will go to the left. So again, we are using invariance. So the situation is really, really the same we saw in the previous slide. Now, I need to be a bit formal here. So I presented to you I would say the main idea, the main intuition. But obviously, I mean, we are doing cryptography, so we need to be formal. So we can define the corresponding problem. The problem are called information set permutation equivalence and canonical form permutation equivalence. In particular, again, you can look just at the canonical form formulation because it's more general. Yeah, so these are the definitions for the problem. What we did in our papers. So I'm speaking about 2 papers. The first one, the authors are me and Eduardo is going to present the paper at AsiaCrypt soon. So in this paper, we introduced this new formulation for the linear equivalence problem, which we call the information set linear equivalence problem. And what's really important, we show that using just this thing about information sets, we obtain a new problem which actually corresponds to permutation to the linear equivalence problem. The proof we give in the paper is very strong because the proof shows that the 2 problems are really, really the same in the sense that if you any yes instance for the linear equivalence problem is a yes instance for this new problem, and the same holds for no instances. So this new formulation is really the same as the old one. So if we apply this technique to less, we don't change the security assumption. The computational complexity of the protocol remains the same because the invariant we are using can be computed in time which is more or less linear in the code length. But obviously signatures get reduced. So this is a direct improvement with no drawback. Again, this whole setting has been generalized in this paper with Tunchu and Eduardo. Obviously, we are also considering the case of monomials. So everything I said can be generalized, take into account monomials. The difference is that the notation becomes really annoying. You can consider failures also for this new problem. You can consider that there are reductions in both ways from and to the standard linear equivalence problem. In the reduction, we also deal with failures. But again, it's just a matter of writing things properly and formally. And also, using this new formulation, we can define a new attack on the problem. The attack is really a collision search. So you have these 2 codes. You produce 2 lists using this invariant, and then you search for collisions. What's nice is that the complexity of the attack does not depend on the finite field size. So this attack really looks like information set decoding because the attacker really just samples information sets. Okay, but again, I cannot tell you details. So if you are interested, you shall read these papers. Yeah, so this is how the problem, the protocol, sorry, looks like in the end. So you see that now, I mean, we still have the very same structure of the protocol you saw in the initial slides. The fact is that now to produce the commitment and to verify the commitment, things get a bit more complicated because now we have to apply, we first apply the transformation, then we do systematic form. After systematic form, we do the canonical form, and finally we do the hash. But really, the structure is the same as the one you already saw. And the fact is that if we apply these new formulations to less, again, we don't change the security assumptions, we don't change the computational complexity, but we actually change the signatures because signatures become really, really short. I have a slide here showing the situation with signatures. So in this slide, I'm considering all the code-based schemes which have been submitted to the NIST call for additional signature schemes. Less is given by these blue triangles, and the graph is showing signature size versus public key size. Now, the triangles I'm highlighting right now corresponds to less FM. So basically, the less scheme without these new techniques. And you see that, for instance, our signatures range from more or less 8 kilobytes to 16 kilobytes. When we apply the information set formulation, and this is actually what we submitted to NIST, the reduction becomes important because we keep the same public key. Public key is not modified, but signatures become much shorter. And indeed now, more or less, the signatures we obtain range from 5 kilobytes to a bit more than 8 kilobytes. When we apply the much more stronger definition of canonical form, then we have really, really short signatures, because now we can achieve signatures that are a bit larger than 1 kilobyte and a bit larger than 2 kilobytes. So you see that if we look at code-based schemes submitted to NIST, less becomes the scheme having the shortest signatures. Well, an exception is Wave, but Wave has much larger public keys. And also I think it is slower than less. So yeah, I mean, this is the effect of using these new formulations. So again, same computational complexity, same keys, same security, but signatures are becoming very, very short. Okay, so I can conclude by saying that I try to explain the main idea behind these new results. What we saw is that we defined some new formulations for the linear equivalence problem. And in particular, the most recent formulation, the one using canonical form, is a very generalized notion for linear equivalence. It also encompasses all definitions. We saw that using this new formulation, we can really reduce the signature size in less, so this is good. But also, I will say, using this new formulation, we have a new view, a new insight, a new perspective on the problem, because we see what's going on. We have new attacks. So yeah, I mean, I think this is good. And actually, I'm continuing studying the problem to see if I can find new attacks. I'm not finding new attacks for the moment, but let's see what happens. Consider that we still have some open problems with less, because, for instance, we have large public keys, because public keys are quadratic. The size of public keys is quadratic in the code length, so it will be good to find a way to reduce the public key size. Also, we need to use Gaussian elimination, and this is costly because the cost is cubic. So if you find ways to solve these problems, it will be really, really good. But finally, we can say that less has very short signatures. So finally, we can claim this after many time and many works. So yeah, this is all. I hope the talk was interesting and not boring. And again, thanks a lot for the invitation. If you have questions, I am here.
Okay. Thank you very much, Paolo. It was very interesting and not too technical. So, any question from the audience, either in person or on Zoom? You can write in the chat as well. Actually, I have a question. So I'm not really in the area. I'm trying to understand. So you prove that the IS LEP problem, basically it's equivalent to the standard linear equivalence problem, right?
Yeah.
What about the new canonical form? Is it a stronger computational assumption?
Okay, it's a really good question. Basically, I mean, the reduction we proposed really depends on the type of canonical form that you have. Because if we look at the formulation, at the formal definition of the problem really depends on how you define the canonical form. Now, the fact is, if we are able to find canonical forms in which you don't have failures, then you can really show that the two problems are really the same. And in the end, the reduction is easy. It's just a matter of linear algebra. I mean, it's annoying because you have to do computations properly, but the reduction works in any case. Okay, so assuming that your canonical form never fails, then really you show that this new CF LEP is really the same as the old LEP. And basically the proof works around the fact that if two codes, you can prove that two codes are linearly equivalent if and only if they are also linearly equivalent considering the canonical form. Okay. However, if canonical forms can fail, then the situation becomes a bit tricky because you have to somehow prove that given any linear code, you can always compute a canonical form for this code. But this is something that really depends on existence of failures, okay? So what we did for now, we were able to find canonical forms that fail with very small probability. So we can say that in practice, our proof works for the wide majority of codes, essentially. But assuming that we are able to find a canonical form that never fails, then yeah, we can really show that this new formulation is really the same as the old one. It's just a different way of writing down the equivalence.
Mm-hmm. Okay. Do you have a lower bound on the size of the canonical form? So how can you imagine how small can you get without violating any kind of information bound?
You mean the size of the response?
Yeah, basically, how small can theoretically the canonical a canonical form can it get? Is there a lower bound? Say, okay, you cannot go below this for this.
Okay, so I'm not sure here. Okay, so my the answer can be entirely wrong, but I think that we kind of reached the optimal size because the fact is that we have this attack. I haven't explained all the details, but essentially the cost of the attack is given by the n choose k, and n choose k corresponds to the no, actually the cost of the attack is the square root of this, so this is a mistake in the proof. But in any case, the fact is that right now, I mean, assuming that we have a code of size, because now the length of the code is 2 lambda, but if we choose a smaller length, then the scheme will not be secure. Okay, so I think that we kind of reached the lowest value, because if we, I mean, if we find something that can be represented with less than 2 lambda bits, then you can have a collision search attack, and the cost of the attack will be less than lambda, because you can always do birthday paradox, etc., etc. Okay, so I think we are kind of close to the lowest possible value, but I don't have a proof. Okay, I'm just thinking out loud.
Okay. Any other question? No. So okay, so then I think we can end here. So thank you very much, Paolo, again. Thank you.
Thank
Paolo.
you.
Thank you.
So
Thank you, Paolo.
see you here,
Oh.
and all the best on your presentation of AsiaCrypt.
Okay, thank you, everyone. Bye.